Okay, so built-in self-test is one of the test mechanism part of DFT now. So here, uh, this is a kind of mm, test mechanism which is very helpful in terms of automized testing environment, so that you don't need a mechanical. I mean, you don't need an engineer to sit and work with the EDA tool to generate the patterns required. So this is a system where you just trigger it like an oscillator. Once you trigger the oscillator, it continuously toggles. So in the same way, this um, BIST, once you enable it, it will automatically generate patterns and it will give you the response. So the internal components are something like this. We have this is a old version. So this is designed in such a way that there is a mechanism created with a finite state machine, FSM. So it will entirely process the data acquisition, okay, and logic identification. Next, it will try to um, target the logic, and based on the logic, it will automatically apply the input and check the output. So there will be a comparator session which will compare both the input and output, and it will give you the output. So output, if it passes, it passes. It's fail, it fails. So that response will get. So you don't need to know what exactly inside that particular IC. Okay, so you can do it directly at the pin of that IC. Okay, so here we have two kind of built-in self-test mechanisms. Okay, we will learn this concept in depth in our DFT sessions going forward. But just an introduction I'm trying to do here. Okay, so there are two types of built-in self-test mechanisms which we can do. One is memory-based, and the other one is logic-based. So the memory-based and logic-based, why we have only two things is because we can write RTL code for combinational logic gates only, and sequential elements and memories. So all the combinational logic gates, including combinational logic gates and sequential logic gates, come under logic based. That means logic. We call it as a logic. So other than this, what are the other elements that we have are the memory IPs. As said, memory. Memory is a we will discuss on memories also from the start when we discuss on that. The type of memories we have, like a RAM, ROM, register files. So whatever you see in the direct physical world is that how much hard disk space is I mean hard disk space you have in your laptop or your mobile or a computer, and any other chip with the memory. So one is the hard disk space, that is a physical memory, and another one is external memories, that are pen drives, external hard disks, and all the memory devices that we have. So all these are comes under ROM category. And ROM category, in the sense ROM is a very initial one, but we have the advanced currently is the latest electrical realizable programmable read-only memories, which are EEPROMs, and more than advanced. The for you guys, your understanding, I'm telling it in your language. because this comes under academics also. So we have ROM and the other one is RAM. So RAM is a random access memory, which is very important in terms of processing that we will learn. A clear understanding of RAM, ROM, and there is one more called register file, and other type of memories. Okay, we'll learn in depth when we learn about MBIST. So for now, that RAM is a random access memory. Random access memory means it is randomly accessed by one major thing. Anybody can answer that? What is RAM accessed by? Anybody? Anybody can try it. In your mobile phones, laptops, and computers, you have RAM starting from 4 GB to 8 GB, 16 GB, 12 GB. Right? You have 6 GB also, I guess. Yeah. So what does this RAM do? Uh, Sorry guys, I don't see the text when I'm trying to present. Okay, if possible, try to uh, unmute and communicate. And anybody did try to attend the session and I did not accept them, admit them. Anyway, let's continue. So RAM is accessed by the processor. Okay, RAM is like to be very practical example, I would say RAM is is designed for processor. Okay, so if there is no RAM, that means there is no execution. You cannot execute any instructions. Okay, so if you have a processor, a CPU, or ALU, you need a RAM, a memory designated for the processing the instructions. Okay, instruction set. So RAM is that particular memory which is designed for that, with the proper rows and columns with a certain sizes. So if you say um, your mobile has 8 GB RAM, so 8 GB RAM, the size of 8 GB RAM would be like 4086, and I mean, so starting from very 8 by 16 and to the 4086, by 4086 or 8048 by 8048. So there will be multiple stack of memories that will contribute, bringing up to this 8 GB of memory, so that it can store 8 GB of uh, memory. So each cell, 8 GB means 8 GB. Each cell has it can store 1 byte of data. So that that many 8 GB cells are placed in small memories, and which are stacked together, contributing the largest, the total size of 8 GB. Okay, you will not have a single 8 GB memory designed inside your device, because the processing would be very difficult. Accessing and processing a larger bit line and word line would be very difficult. So we make them into small clusters and use them in our real time. Okay, so these type of memories, RAM and ROM. ROM is a read-only memory. I mean, the naming is read-only memory of the type we say, but it's a type of memory where we store data like our hard disk. Okay, so there is another file called register file, RF. Okay, so register file is also a type of memory which is the close to RAM. Okay, so this register file is also considered as a memory. We test it, and register files are pretty much used in the design of cache memories. Cache. So cache memories are cache is a. I'm not sure how many of you know what is cache memory, but I would say it is very common now because every mobile nowadays will show you have a basic optimization um, app or UI that is provided by the OS. So that will give you the option to clear the cache every time, right? Even in the system, people use CC cleaner and other thing um, to clean the um, all all the cache that we this processor lives in the process of execution. Okay, starting from invoking your laptop. Once the laptop or a computer is on or a mobile on, since then till you shut it down, whatever the has executed instructions. Okay, that means his user has opened multiple apps, he has used them. So the processor uses cache to store every execution process in the cache. So that will leave a lot of cache data. But caches are not in bigger sizes; they are of very small sizes. Hardly, you would say. Now, I mean, if it is a supercomputers, will have higher caches in terabytes. But in terms of mobile and laptops, what we see is hardly having three caches with 16 MB. So L1, L2, L3. Uh, I'm not sure. Those who have expertise in computers, they might be aware of this. Okay, so cache memories are designed internally with the register files. They are more convenient in designing. We'll get to know more when we learn MBIST on this type of memory. So these memories are designed with a technology called programmable array logics (PAL) and um, PLA. I'm not sure. I mean, I don't expect everyone to be from electronics background, but if they are from electronics background, they might have covered this where uh, you have learned on this PAL, PLE, and CLB, the combination logic box from FPGA and all. So the design of memory starts from that array of memory cells packed together to contribute storing memory and I mean the data, one bit of data. So for each cell. So how do you access that all together in the form of rows and columns, and in the FIFO fashion? So all that is from uh, computer. I mean the computer organization subject or from VLS subject. I'm not sure where it is in academics. It's been a long time for me. So to test that, you need a mechanism separately, something like this. You see here, it's little blurred, but the image is little blurred, but still uh, visible. You see that there is a RAM which has the address port, data in port, control, data out. So address data in control are the input pins, which are the control signals of this particular RAM. That means you can access RAM memory through these pins. So this is the additional logic that was introduced by the built-in self-test mechanism along with the FSM and the comparator, whatever you see outside this entire thing. Okay, so these particular RAMs are included or instantiated as part of the RTL coding. So the RTL engineer has to write this. Okay, if he is writing, for example, he is writing code for a CPU block. CPU is a central processing unit where it is the processor core, the core processor cores. Okay, CPU is a processor. Okay, now if he is writing for that code, okay, CPU has registers, data registers, address registers, and RAM should be called in, which is linked to the CPU of these data registers, address registers. So all are interlinked. So while writing RTL code, you represent that particular memory IP for the data storage in terms of communication between um, the CPU and the RAM. There are multiple internal caches also again. So all this stuff, okay, this is a communication between the processor and the memory. Okay, so it is already there in the RTL code. While RTL engineer is writing, he has to do that. Now, this is already connected to the logic. So while writing the code, he will write the code module, and along with that, he will try to show that, okay, this logic output is connecting to this address directly. Okay. Uh, See, let's say this mux is newly added by the BIST logic, but without this mux, previously, this logic is directly connected to this address pin. Okay, likewise. So data out is directly connected back to again this logic. Okay, so this and this is already having connectivity. What you try to add is the additional connectivity to have a bypass. Bypass means this is a functional path and this is your testing path. So when you just add a mux to gain access to the same pin by not disturbing the functional path, so that you can have a select line of this mux, which will give you which will you say which will you which you will say that test mode. The select line is connected to a test mode signal where you will say mbist enable or mbist disable. So if mbist enable is high, this functional mode will not be disturbed. It will directly use this test mode signal. If functional enable, sorry, the mbist, okay, memory testing is disabled, that means this line will be disabled and it will choose this particular input and it will function as normal as that. So one important rule here in DFT is that you never change the functionality, optimize the functionality, okay, alter the functionality or disturb the functionality in any way. Okay, because the uh, the functionality is written by the RTL engineer, RTL design engineer, and it's a design. It's as per the required design requirement, and it is freezed. You don't disturb that. It is the work of RTL engineer to change the code at any point of time. Okay, so you as a DFT engineer has to add an additional logic by adding muxes on the all the logic that you want to test, either it's a memory or the logic, but you will not touch the functionality. There's a golden thumb rule of DFT: do not disturb the functionality. Okay. Now these memories, um, need to be tested, because you don't know this 8 gigabyte of RAM memory. It has 8 gigabyte cells. Each cell withholds uh, one bit of data. So this one bit of data is either 0 or 1, correct? So your 1, 0 or 1, it should not be stuck at a certain value. That's what you verify. You make sure that the entire RAM cells are accessible for read and write, and you are able to change the value of from 0 to 1. Okay, once it gets manufactured, it will work as per the regular process of CPU to RAM connectivity, and it will CPU, when CPU starts working, it will store data and use the RAM for its fetch, decode, and execute process. So this is a regular process of, once it is manufactured, it becomes a physical IC, and it is enabled. When you power on your mobile, the real functionality starts. So when it is still in the before manufacturing, when you're trying to design it, okay, you have to, as a DFT engineer, have to make sure that, okay, each and every cell is accessible, read for read, write, and they are not stuck at a single value, either to the lower grounded or connected to the high value. The way, either VCC or VDD, it should be connected properly, and the value should be changeable of that particular cell. If it is not changing, then it's redundant, or it has an issue. You have to identify it and fix it. Okay, that's the work of the DFT engineer in terms of memory testing. Now, that is a process how you test memories, and that is memory based. Coming to logic based. Okay, logic based. Let me see if there is an image for logic based. I don't think so here. Okay, we'll discuss logic based with the proper example next time. Uh, in theory, I will say that logic based is something where you have a AND gate, NOR gate, OR gate. So you have close to 1 trillion, or more than 1 million or 10 million combinational logic gates in your SOC design. That means in your IC. Now, your work as a DFT engineer is to prove that your entire SOC or IC having these combination logic gates and sequential cells are controllable and observable, and these are, there is no stuck it. I mean, they are not stuck to ground or high. That is the one type of fault category I'm talking about. And one more fault type of category is where transition, that means the real time computing with time. When you say time, that means the if you have allocated, okay, if you have allocated 1 nanosecond for one flop, okay, so that means logic doesn't take much time. The transition time in between the combination, inside the combination logic gate, is less, but each sequential cell will take 1 nanosecond of time. Okay, on top of it you have setup time and hold time to make the value stable. Okay, so there will not be any rush between the data transition or data loss. Okay, that we'll learn in the concepts. Okay, guys, I don't want to confuse you guys. So let's say from here, this point to this point, let's say I've allocated 1 nanosecond, then within 1 nanosecond, the value has to come here. That is real-time computing. So if you say that the data has to come within this time, then it has to come. If it is not coming, that means there is some issue in from this path to from here to here. from source to destination, you have a, uh, some delay in the data path. So you will see and identify, okay, for this transition, that is a the fault type is transition fault. So that is one category. So entire world semiconductor first verifies these two things. One is stucket and another is transition. So one is stucket is where the logic value and get input or output is not tied to low or tied to high. That is stucket. Transition is where the data, okay, for and gate, you are giving some value input, 1 and 0. Okay. So AND gate output comes as 0. So to give a value to AND gate, you need to have a storage element first. Through the storage element, you will be able to put some value there. So you have a flop. Let's say you have a flop in the inputs of AND gate. So you try to drive one value to the one of the inputs of AND gate, and another input of AND gate B, you are trying to add uh, drive 0. So 1 and 0 will become 0. So this particular entire operation should be done within certain period of time, and it has to be done. So the transition has to happen with the expected time. If the expected time it is not done, then there is a problem. So we have to find what is causing the delay. So these two are tested, okay, in a scan insertion flow as well as a logic BIST flow. So when I'm talking here, we're talking about BIST. So you can automate this scan insertion flow by logic BIST by same BIST mechanism. How you are using it for testing memories, you test it. You use it to test the logic also. So again you add simply you add muxes at the inputs and try to get output. So remembering the thumb rule that we should not disturb the functionality. So both this memory based and logic based um, are something that built-in self-test mechanisms run by FSM. So both of this has to work. I mean, you can work it out MBIST and LBIST for any IC using JTAG. If there is no JTAG, you cannot uh, do anything inside IC. That's true. If you do not have this IEEE 1149.1 standard for boundary scan test, and you don't have this tab, test access port, which is giving you the finite state machine. So the finite state machine sits in this test access port logic. So this is JTAG, Joint Test Action Group. So these are the founders of IEEE. Uh, so they have introduced this when chip came into existence. When chip came into existence, okay, when chip came into existence, the IEEE and Intel founder was also part of that. Never mind that. So these people have introduced that you need some logic and FSM to uh, control what's happening inside the IC to the outside world, so that you can gain access from directly from the pins. Okay, will have more flexibility, okay, through the proper FSM. If you have FSM, you can test the interconnectivities between multiple blocks inside your IC. So that's JTAG, the work of JTAG. So if there is no JTAG, the internal components are this BIST. MBIST or LBIST or scan, anything for that sake. If you don't have JTAG uh, at the top of SOC in the sense at this level, at SOC level, considering this is a chip, full chip SOC, and you have multiple blocks inside, CPU, GPU, display in it, all of this, then it will be the at the top. So you have to have this JTAG to perform anything post manufacturing or pre manufacturing. So for pre manufacturing testing or post manufacturing testing and debug and diagnosis, if you don't have JTAG, your IC is as useless that you will not be able to access it once it is designed, just use and throw. And you will not able to test also. Okay. So that's uh, the importance of JTAG in DFT. So all of you have to learn this JTAG insertion very clearly and precisely. We'll learn that and we'll do multiple labs and exercises on this. So till this part, everyone are able to understand the overview? Am I clear? Any queries? Guys? No queries? No. Okay. Okay. Fine. Moving to the another stage within the ASIC flow is a synthesis. So everybody has to know what is synthesis. So synthesis is something it's a very required process, and you use the EDA tool to synthesize it. Okay, so if you're very good in understanding the process synthesis, you can write synthesized gate level code for the given RTL code. We used to do that in very old times in between 2000. I mean, even in academics, I used to do that. I used to be very good, very low coder at the time. Luckily, my HOD is very strict. So, very low code, you know how you write very low code. So you once you write very low code, it's very easy to convert into gate level. So, but when you have a larger designs, you cannot do it manually. So you need a you need to depend on the EDA tool, synthesis tools. So synthesis tool is a EDA tool. In the market, we have two major synthesis tool vendors. One is Synopsys, the other one is Cadence. And there are many other third-party vendors who still do synthesis, but not majorly used in the what we call the official semiconductor. Okay, so we'll be also using Synopsys in our labs. So Synopsys synthesis tool you will get to understand more when you work on that. So whatever the RTL code you have written, that's a code. You have written, okay, module and gate, input, output, okay, and behavior. You will write the behavioral code and end module, done. This is code. Now, converting this code into the gate level. Gate level is something here in this process, you have to provide all the library cells of whatever you have used here. Okay, what you have mentioned here, like for example, in writing the code, you might have used uh, C is equal to A and B. That means the output of A, the operation of A and B, you are saying it in C. That means you are asking the tool to convert this RTL code into proper gate. That means tool will ask, okay, I need the library model for AND gate. No, AND gate, if it is a two input, one output AND gate, okay, then you will have that module definition. Okay, library means module definition. Remember this, when you say library, there's a module definition of that particular cell. If you say AND library cell or combination logic gates, all combination logic gates and sequential gates. So when you say library, that means the particular uh, m- uh, behavior as well as the uh, functional logic of that particular cell. Now you need to provide that library so that tool will try it again in a proper way that, okay, AND gate, this is the model. Okay, I picked it from the library. So tool will very precisely show this is the AND module provided in the library. So you are instantiating that particular original module, okay, and you are using it in in your code. So this is the A input, this is the B input, and this is the C output. Okay, so this AND gate is connected to the previously one more OR gate or some other gate, so that output is connected to the A, and this AND gate C output is connected back to again gate input. So all these connectivities are properly formed in gate level netlist. So if you have a gate level netlist, is more convenient for the next stages, because ultimately you have to work for gate level only. So even when you say, if you take the RTL flow and netlist flow, if your RTL flow, if you are going with RTL flow, once RTL is given to physical design team, even physical design team has to synthesize it to gate level to proceed further, because the physical design team cannot work on direct RTL. Remember that they have to synthesize it first to proceed to the next stages. Entire physical design flow is entirely done on a gate level netlist. Okay, because they have to do a physical layout. Physical layout is done only on a proper gates. If you know, okay, this is the they have used this gate. Okay, this library model for AND gate, this library model for flip flop. Okay, so they have to know that with the proper library synthesized gate level netlist. That is synthesis. Okay, that process is called synthesis. So this synthesis is done by EDA tools. Okay, now coming to what we have here is ASIC vendor provides cell library of basic gates. Yes, whatever that I mentioned now. So it will be providing for every component, okay, or element that you use in the RTL code. Okay, so without these components, you cannot write RTL code. What you will write for? You will write. If you are writing for a full header or a half header, you have to use all the gates. You need all the gate libraries to convert into gate level. In RTL code, you will just write and gate, or gate, and gate, all this stuff. Okay, but you need all these libraries for these gates. Okay, now pre-synthesized IP core blocks are treated as black box. So pre-synthesized IP core blocks. What he meant is, in our previous session, we discussed the IPs, the intellectual properties. So if you have a IP purchased from some third-party vendor, so he will give you a synthesized version and a raw version of RTL, everything. So when you have a synthesized version, you will directly plug and play. You will just use it. It's a pre-synthesized RTL. You have it, and you will use it as a black box in your existing execution, because So here, when you say black box, that means empty module. Okay. So you don't worry about what is inside this intellectual property, because IP, when you say IP, that means it is secured IP. You have secure and non-secured IPs. So secured IPs are something where hard IPs. Hard IPs, when you say, they are just plug and play. You cannot modify the logic inside that hard IP. Okay. When you cannot alter or change the logic or look into that logic, sometimes if it is more secure, that means let's say Intel and Intel competitors are ARM, Qualcomm, okay, uh, and AMD, Nvidia. So even their competitors in real time, you work with them. You accept projects from AMD, you accept projects from Nvidia, you work with ARM, so you use ARM IPs in your associate designs. So when you do that, okay, when you the other vendor is a competitor, why would he reveal his internal code? Okay, okay, so everyone has their own secure information in that IP. They don't want to reveal to the competitor, okay, or anybody else, not just competitor. In the market, everybody is a competitor when you are in the semiconductor domain. So what they do is, few people will say this is not open source. Okay, see, remember this again: open source and secure IP. Open source is something. Okay, this is a RISC-V. RISC-V is a open source design. Anybody can use it and customize it. Okay, there is a memory. As I said, there is a 8 GB memory. Okay, likewise we have 4 GB, 8 GB memory, and each split into 1 kilobyte, 1 KB, or 1 GB. Likewise, there are multiple memories purchased from Samsung. If you have a synopsis, if your synopsis is a synopsis and cadence are the major vendors of these memories, along with the TSMC, just for an FI. So when you're purchasing them, if you have to sign a bond or a contract for the IP security and confidentiality, so that you say that, okay, you're using my IP, and make sure you don't reveal this information to outside world. You just use in your SoC design, and you're done. Finish it off. You should not reveal any of the my IP that you purchased from to outside world or competitor. If the information or the IP that I have sold you is going into any of the my competitors' hands, then you are responsible, and I'll file a lawsuit on you. This will be the agreement. Okay, this is very clear and precise agreement everybody signs when you purchase third-party IPs. So few people will say, do not go inside my IP, just use it as a black box and stitch. Black box means you will have only input and output ports of that particular module. Let's say it's a full adder. So module full adder, it's a 16-bit full adder. Okay, 16-bit full adder. Inputs and outputs are only present. You cannot access the logic of this, the functionality logic and the behavior of that particular IP, the full adder. So you tell the tool, okay, this is the black box module. Tool has a syntaxes where you can tell the tool that, okay, this is an IP and this is a black box module. So consider it as a black box module, and I will give you the library for this particular full adder without the functional logic. Only I will give you input and output ports. So treat it as a black box and proceed with the processing further. Okay, so that is how it is done when you have a pre-synthesized IP. So we'll learn more on this black box and IP when we do, okay, labs. Now, some of the popular synthesizers are, yeah, Synopsys DC, Design Compiler. Again, the Cadence, Ambit, Bill Gates, these are old, man. Um, I think this document is pretty old, but Synopsys DC and Cadence are the same. Simplify ASIC is still there, but um, we don't use it in semiconductor as of now. I mean, the major companies, nobody uses it because it has to approve. Fab has to approve any tool that you are working, because EDA tools are customized as per the fabs. Okay, everything will go as per standards, as I said, right? Everything has to be as per standard. Something like TSMC, you're ultimately going to manufacture your IC in TSMC fab. You are taking libraries from TSMC. Your EDA tools also has to support that and be in terms and lines with the vendor. I mean the fab. Okay, so it will be customized as per that particular fab. Your EDA tool will be customized. You have to tell the EDA tool, okay, this is the TSMC will be your fab. Intel is your fab. Samsung is your fab. You have to specify it. So the tool will use the default settings already stored in the database of EDA tool, that will make a compatible version for that fab. Anything that is executed in that EDA tool will be compatible for that fab. Okay, so even 20 years back document, if you see of the DFT, things will not change as per the functionalities. Pretty much it might have advanced features, but the old here there is no change of the fundamentals. Okay. Mm, this is a synthesis script which has the directives of for synthesizing. So how you tell the tool to synthesize. I mean, the goals of synthesis script is to optimize. These will be very heavy for you guys. I don't want to go with this. Let's see what else we have here. Special care should be taken for high fan mode nets like clock and reset. Yes, because clock and resets are the major uh, major control signals of all the flops in the design, which plays a key role. Entire SOC can go into trash bin, just if one particular clock or reset is not functioning as per the requirement during testing. Okay, it has passed everything at our side, and when you go to the tester and you say that one clock is not behaving as such, you're gone. That clock is gone. That means you are expecting a 2.4 gigahertz or a 4.8 gigahertz frequency clock speed, and it is not giving that. You just make a lower version of it nowadays. So whatever it is giving, for example, it is giving only 1.2 gigahertz. Okay, you can make market with 1.2 gigahertz of that particular IC. Okay, fabricate it. Then you will say that, okay, what you will make is, so your intended full clock speed is 4.8, or let's not take 4.8, let's take 2.4 gigahertz, and you did not meet it. But 2.4 gigahertz is for a high-end RAM memories within that IC. But you also have low end. I mean, as I said, it's a group of memories that will bring you that size of memory, the total size. So you will not have a single memory file with a 8 GB of RAM. No, it will not happen. You will have a clusters starting from what we call the lowest size, 8 by 16 is the lowest 8 by 8, and 8 by 8 I think is the lowest memory size I have seen, the smallest file. with the rows and columns, 8 rows and 16 columns, or 8 rows and 8 columns. So when you say that your intended 2.4 gigahertz speed is for a 8 GB RAM, okay? Now this 2.4 gigahertz is what? It's a CPU clock, and your RAM is expected for you need that speed to be matching with the 8 GB RAM. Now you say that post manufacturing or during testing, you've identified that okay, this is not as expected to be for 8 GB. You're getting only 1.2. Then what you will do? Then you will do that. You will half it, 4 GB. Okay, you're able to access 4 GB now. Okay, disable the 4 GB RAM memories out of 8 and use only 4 GB memories. So you will have this kind of features also with DFT. So what you do is okay, in you when you go and purchase mobiles or laptops in your I mean in a digital media or any shop, what you see starting from the lower versions of 4 GB, 6 GB, 8 GB, 10, 12, 16 GB. Similarly, the RAM and ROM go along, and every time the RAM or the ROM increases, the clock speed increases. You can identify this. Okay, so that lower version, you are coming to that lower version. That doesn't mean every time it is because of we are not able to meet the expected frequency after post manufacturing. Not entirely always the same, but that is also the case where the manufacturers will decide that okay, uh, we try to ship out what we call 300 ICs from a single silicon wafer. Then out of 300, you see that only 200 are working as per the requirement, 100 are not working due to the PVT corners, the process variance and temperature corners. We'll discuss that later, okay? But I'm telling you, so not all the silicon wafers, I mean, entire silicon wafer that you see as the round circle wafer that you have seen previously in our slides, that will not all the, I mean, entire XY corners entirely of that wafer will not respond to the full voltage or the current parameters. So IC parameters are not met at every corner of that wafer. So only few are met. So I'm not sure I have shared that in any of the in our previous discussions, but we will discuss that going forward. Okay, I'll show you how it is why uh, not all corners are met for the expectations in a single wafer for manufacturing. So when I say that it is not met, that means in the center of wafer it is we are getting 2.4 gigahertz. In the corners you might get only 1.8 or 1.2. Okay, and it's not stable. So how much is stable, how much is unstable, that all we consider, and we try to downgrade and use it as a low end device. Why to waste it? See, you have found that out of 300 you 200 is working as per expected and 100 are not expecting. You want to throw them. How much loss for the manufacturer? Why would he do that? When you have this feature to enable or disable few memories and the clocking speed, adjust the clocking speed accordingly, you will do that, right? You will do that and sell it as a low end version. Why would you trash entire stock of manufactured ICs which are underperforming? No, you will not do that, right? So it's a huge loss in terms of billions of crores, okay, of money. So that they will not do. So they will try to release low end versions. So whenever you buy, I think now when you see mobiles of low end versions in the market, I'm not sure you will buy them, but See, uh, this is a reality, but true. That's the reason why every time I buy the high-end version, because I know the process of designing and manufacturing. So this is how it works in reality, and uh, you have to take care of it. If you do not take care of uh, clocks and resets properly, your IC will not perform as per required uh, post manufacturing. Okay, next. So this is pre-layout timing simulation done by the physical design engineers. Let's not go into this because this is not required for you guys. So setup violation, hold violation. Um, it will be heavy for you now because many of you are new to this. This we'll discuss once we go in depth. Okay, I'm not going to discuss it now. Okay, so DRCs, design rule checks. So in DFT or physical design or any of the semiconductor domain, one thing you will hear where engineers are stuck or spending time, huge time in working for the semiconductor domains, day and night sometimes during project executions or tape-ins or tape-outs. The only reason is DRC. They have to clean the DRC to proceed further. If you have DRC, then you cannot tape in. So DRC means design rule check. So who gives this design rule checks? Who gives you this design rule checks? Anybody? Or anybody can explain why these design rule checks? Why do you need design rule checks? What happens if you don't use have design
Error
rule checks?
checking.
Error checking. Okay, so here we are in the digital world. We are talking about semiconductor design rule checks. Now, in what aspects would you see that errors in a design with the combination logic gates and sequential cells? What would that be? Yeah, see, even it's silly, you can say no problem. Everybody's learning here.
Verify specific design like improved by the process technology.
Hmm. Yeah, I mean, you're asking or you're telling that?
The design rule check I am telling.
Okay, you're telling for design rule check. So, um, if you, I mean, in the previous slides also there is a hint that I mean, just this previous slide, I have given a biggest explanation what happens if these things are not taken care. What are those? Just previous slide, we discussed what happens when you don't take care of these two things. The post manufacturing, you have to derive the underperforming the low end version of the expected design. What were the two signals?
Clock and reset.
Clocks and resets. Right. Now, your entire design, okay, entire design, you will have combinational and sequential cells. And they work with 1 and 0, right? They are working on 0 and 1. So ultimately, any combination logic gate input has to be driven from either primary input of the SOC. Primary input means the direct pin, okay, or it has to be driven from a flip flop. Now, when you write the code, you mention that, okay, I need one bit of data coming out of this AND gate. Let's say you are doing full adder. In full adder, okay, you need to store every combinational output coming out of each row, right, to be fed to the next row, and you take the final output. So when you want to do it in a real time, you definitely will allocate one register for that. So you will write a register for each and every uh, output. You will allocate one register, and for every possible input also you will allocate registers. So the best DFT friendly netlist or RTL or design will be when you have more number of registers, okay, and every register is doing some input, taking some input or driving some output. So when you do that, your entire design is dependent on the flip flops. Okay, so these flip flops are controlled by D input, clock, set, reset. Correct? Everybody agree on that? Everybody has idea of D flip flop, right? So if a D flip flop, it has D input, data input, clock, and a set and reset. Now, if you data input is anyway, that is evident that we drive in data, toggle the data in and out. Now, clocks and resets are the main control signals. So entire SOC design, if you take the control signals of this logic, are nothing but logic and the clock, set and reset. Now your entire DRCs will be designed based on clocks, set and resets only. What the tool will say, this is a DRCs are evidently provided given by the tools. Tool will throw out this error. As I said, you have to use the tool to do anything in the semiconductor, and the tools are compatible with the foundries. Foundry means the fab. Okay, so the particular foundries, I mean, the tools are having all the default settings of this DRC is designed predominantly based on the foundry inputs. It will say that, okay, clock to do DFT, these are the DFT rules, pre DFT, post DFT. So pre DFT rules, design rule checks are okay. In order to convert this entire design into DFT friendly or scan inserted design, I have these rules. The tool will say, okay, now what are the rules? The data should be, the data path should be very clear. Clock should be driven directly from the primary input. Reset should be controlled directly from the primary input. So all these kind of rules are nothing but the design rule checks. Now, these are the rules. When the tool tries to check it and throw error, then that becomes the design rule check, and it will throw, okay, DRC C1 violation, DRC, okay, data rule violation, reset violation, set violation. All these violations are entirely on clocks, sets, resets, and data. Okay, clear, right? It's clear to everyone. Any queries here? Okay. So the gate level netlist must be checked for design rules before starting backend design. Not just backend design, any design. For front end, backend, every time we do, the tool will do that. And we ask the tool to perform this design rule checks because we don't trust the tool. That's the reason engineer is hired. Okay. Engineer is hired, the reason we don't trust the tool yet. So even we if we trust the tool, we we cannot give the keys to the tool. Okay. Engineer has to be there, and otherwise it will become a nightmare uh, for the human beings. So we don't give the keys to the machines. So that will not happen. uh, so what happens is these tools are pretty much designed by us to ease the operations, so that engineer don't need to work years and years to uh, process things. Okay. If an engineer has to work manually without the tools, it will, for the current technology node that we have with the complexity, we would never have come to this level of 1 nanometer, 2 nanometer, 3 nanometer technology nodes, and we would never be using these smartphone devices now if there were no tools. So EDA tools are the pillars of semiconductor, and they are like a gods. Literally they are gods. EDA tools are the gods. Without EDA tools there is no semiconductor. That's very clear. Now EDA tools are controlled by the design engineers or the chip design engineers from front end to back end, and control them through the tool commands to say ask for, okay, I need a proper SOC. For a proper SOC design, what you need, okay, these are the design rule checks mandatory, you have to do it. So you will tell the tool, okay, perform DRC checks. Okay. After perform DRC checks, if there is no DRCs, you will write a report out of these DRC checks and you will verify it. Okay, everything is fine. Then insert DFT. You will tell the tool to insert DFT. So tool will start inserting DFT based on, before these two steps we have a lot of commands. We'll provide what are the clocks, what are the resets, what are the inputs that you want to give to the tool, because tool is something like a uh, coffee machine. You give milk, you give coffee seeds, okay, water, and you tell, oh, you want a cappuccino, lasano, anything, or just pure milk, you have to tell, and it will give you out, right? So similarly, here you have to give the inputs of netlist, libraries, the clock constraints, reset constraints, all of it, and you tell the tool, okay, I need a DFT insertion with a demux flops and a mux design. All of these parameters, there are many parameters scanning session. So you will tell all of this, and through commands, and you write a tickle script. You write a tickle script. So all these commands are, I mean, the tools are compatible with tickle scripting or a shell scripting. So shell scripting is old, but tickle scripting is very prominent. All EDA tools are compatible with the tickle scripting. But don't think that tickle scripting what software engineers uses is the same. That is entirely different. Okay, our tickle scripting is very easy, and we use it to help the EDA tool understand things. That's it. So it will be very, mostly it will be for each commands and if else statements. Very basic. Even a 10th class student can learn while execution. Okay, no need to worry on that. Now these commands, you tell the tool and you make the tool to execute. Okay, so you do checks pre DFT and post DFT also. Okay, pre DFT, okay, all you have check the all control signals are intact. Okay, post DFT, okay, insertion is done properly, connectivity is done clearly. Okay, then fine, you write out the scan inserted design netlist clearly. Okay, so likewise in backend in physical design also they have these all whatever you see here, different DSS or LSS, all are physical design related DRCs. Okay, so we don't want to learn this backend. We are not learning physical design here. So even where DFT comes in, I just want to help you guys understand. We'll just talk a little bit here, but we are not going in depth of physical design flow. But we have to know backend design how they do, because they have to do with the help of DFT. Without DFT, backend cannot perform with the current ASIC flows that we have. Okay, because tool will ask. Tool also has option that it's an option again. There is even still there are many ICs that are done only with boundary scan but no DFT. They don't want it. That means they don't want DFT because that IC is not that credible, or it's a smaller designs, or it's just a use and throw design. No need of post manufacturing debug and diagnosis for that particular IC. Then the vendor will ask, okay, the client will ask, I don't need DFT. I don't want to spend time, money, and time on the DFT. It's a small IC. It's a not reusable IC. Then it's good. Okay. Then in the flow, we will tell the tool, okay, we'll switch off the DFT switch. Okay. For physical design, I'm telling, because now if DFT is not there, directly RTL physical design will directly interact. Okay. So now when you have DFT, this is the flow where your scan insertion done, DFT netlist is given to the physical design team after you do scan insertion, the DFT inserted netlist. Then they start floor planning, placement, and routing. So in between placement and routing, you have these many steps. See, placement, where you do scan chain stitching and ATPG DFT properly, clock tree synthesis, routing, and annotations, back annotations with the RC delay extraction. This you will learn, guys. Don't take it too much on your head now. Okay, this is the flow. Okay, this is the last slide before we go into another topic. Okay, now scan insertion. This is our actual stuff. Okay, and even here we are not learning the full scan insertion, guys. This is a pre-layout. I mean, the just overview. Okay, all internal flip-flops and latches are replaced by scan flip-flops. That means whatever you see here, this is the actual design. Don't misunderstand this. In semiconductor, we use a cloud with a cloud's shape, or this kind of shape representing the logic. Okay, this means here we have all the combination logic gates. Gates. Combination logic means gates, and gate, non gate, and not all the gates. Okay, that comes in here. Here. Now, these are the flops, flip flops, sequential elements. So this is the actual circuit before scan insertion. Let's say, let me go inside this little bit to explain what is happening here. Okay, everyone can see this, at least what is happening here, because I want to. I'm going to explain this diagram. Okay. Now we have combination logic with the A, B, and C inputs. Okay. Now A, B are primary inputs. C is also primary input. Okay, primary input is something that that particular partition level pin directly from this level. This is your SOC. Then it is this SOC pin, direct pin, you are able to give as input value to this. That is called primary input. Okay, and primary output directly to this here. Now, A, B, C are primary inputs, and out1 and out2 are primary outputs. In between, you have a lot of combination logic gate with the sequential cells. Now, what is happening here? A, B are directly going as inputs here. C also going direct input, and one of the C is again going to this flip flop, and this flip flop output is again feeding into one of the inputs of this combination logic gates again. Okay. Now, this flip flops is a sequential. They are connected in a proper sequence, but not shift registers, but in a sequence based on a single clock. They are driven by a single clock. Okay. Till this part, it is clear by to everyone. I want response from everybody. Till this point, it is clear to everyone.
Yeah.
Okay.
Yes, sir.
Now, so this Q output, this is data input. C is going as data input here. Q output is going to this combination logic. So somewhere A and B is going to one input, one AND gate, and AND gate is a single output. Okay, and again this Q output is going along with the AND gate output to another OR gate or some other gate. Assuming, okay. Now that another gate output is again getting being fed to this flip flop again to the D input. Okay, because flip flop, this is input, this is output. I hope everybody know that. So something is coming from this combination logic gate, it is getting fed here, and this Q output is again going back to this combination logic gate. Again, some other output of combination logic gate is coming directly to this sequential cell flip flop to the D input, and this Q again is going back, okay, and going to one of the combination logic inputs again here, and finally we are getting output from this. Similarly, one output is coming from here. Okay, this is the understanding of a combination logic gate. You have to spend some time to understand this logic. Okay, not so complicated. Don't assume everything to be complicated. Think that everything is a piece of cake. It's easy. Okay, when you see things in a smaller size, then only you will be able to understand. When you see everything as a bigger sizes and shapes, then you will not be able to digest it. First, you will get a fear of consciousness where, oh, this is complex, or I'm not able to understand. So that fear comes out of when you are not setting your brain to see things in a smaller size rather than in a bigger way. Okay, think that, okay, any issue, take it in a small easy way, then only, and see it again. The first view, you feel that, okay, it is too heavy, too complex, I cannot take it. Now take your time, breathe in, think it in a very small. Try to what everybody know how touch works, right? Finger touch of screen, zoom in, zoom out. So if you want to minimize a image to smaller with your fingerprints, how you will do it? Slowly you will touch the image and you will try to bring all the fingers, expanded fingers, to smaller, nearer to smaller shape. So keep that in mind, because going forward in semiconductor, when you're working on a larger SOC designs or any design which have lots of combination logic gates and sequential cells, you will have to see some schematics where you will see lot of logic, okay, connected one to one in a proper connectivity. You should not be afraid or feel that it is too complicated. Okay, make it small in your brain, not okay, not in the screen. make it in screen. If you make it small, you will not be able to identify what is what. So in your brain, you have to make things small and see. Okay, this is just my personal advice. It's up to you guys. Now, post scan, after scan, what you add is you add an additional logic. You add a mux into each flip flop. You add a mux. Why you add a mux? I have explained in one of the previous slides. Why you need a mux? What is the functionality of a mux and why you add it? What what happens? I mean, what happens if you don't add mux and what happens if you add a mux? Anybody has a idea? Just can tell. I'm telling directly that it's a mux that we add to every existing flip flop. It's a D flip flop. Before scan, it's a D flip flop. What you have is a D clock Q and a set reset. Okay. Now post DFT insertion, what we do is add a mux at the D path. So why we add it? What is the purpose? What what if we don't add it? Anybody has an idea? I have already explained in, I mean, I have given a hint of the purpose of these marks in previous slides. During BIST explanation, I try to explain, right? Why is mux added? What happens if you don't add mux? Anybody? Try to recollect. That's why I say that please pay attention to the class. Don't depend on the recording.
Several data inputs collecting
Mm,
and
I mean, inside the flip flop. So it's it's very clear that we have D flip flops here. We are adding one more mux inside D flip flop in the D path. Okay, sorry. Okay, in the D path to convert D flip flop into scannable flop. Okay, we are converting all the D flip flops of the existing functional D flip flops into scannable flip flops for our DFT purpose. That is the additional test logic that we are adding. Okay, so I'm asking anybody has an idea of the purpose of mux? Why we add a mux to one path? What is the functionality of this mux? So just say that
to reduce
if
the logic.
yeah, what is the functionality of mux? You can say what are the inputs of mux and outputs of
Maximum
mux?
input, maximum input, one outputs.
Maximum inputs and one output. Let's say that two input, one output mux. Okay, now two input, one output mux. You have a select line, right? Single select line, which will select A input or B input of that mux. Correct? That's the way mux behaves, right? You select the input pin based on the select line. Correct? Everybody agree on that?
Yes, sir.
Now, as I said, we don't want to disturb the functionality. Now, you guys able to recall? I told this before, right? We don't want to disturb the functionality, existing functionality. So this is existing functionality code written by the RTL design engineer. Okay. Your DFT logic should not disturb the existing functionality logic at all. At all. To make sure that this logic, functional logic is disturbed, not disturbed, we do functional uh, equivalence check, formality equivalence checks. Okay, guys, equivalence checks we do at every stage of DFT physical design to make sure that we did not disturb any functionality of the design, either DFT or physical design. Both has to do that. Is it clear? Clear to everyone? Respond, guys.
Clear, sir.
Okay. Now, when you add a mux here, what you are trying to see, if you want, see, if you want in digital design, if you want to bypass existing path, this is one data path, right? This data path, any path, if you want to bypass this existing path, any existing path can be bypassed and added one more additional path on top of the existing path and give a controllability to select the path can be done by mux, by adding mux. The main intention of mux is the same. Mux was designed for that. Okay. Mux might be useful in many ways, but the main intention is that add one more path. Okay. You get multiple inputs and you can select which input you want. Okay. Now you need a scan path for DFT. That means like this. Scan input. SC means scan input. In a shortcut, it is written like this. SC in, okay, SC in, SC in, SC out. Finally, this is a chain formation. Okay, now what we have done is we stitched all these three flops in a chain format, like a shift register format. Okay, I'm trying to even, I will discuss scan session again, but I'm trying to explain here itself what we do in scan session. Okay, with this small logic, I'm trying to explain you guys. Try to concentrate and ask me if you have any queries. Now, you need a scan path. Why you need a scan path is a question you should get. Okay, why you need to add additional logic for DFT? Why you need? Because you want to test the functionality. You want to, as a DFT, what you have to do is you have to prove that this functional logic is fault free. Fault free means in previous sessions I had previous slides that I explained, we have stuck at fault. That something like D input is not grounded, clock input is not grounded, or clock input is not directly tied to the power source. Clock is not directly powered to the power source. Illegal connections or anything. I mean, this can be verified by functional verification also. Okay, but functional verification will not verify the internal connections. He can directly verify the A, B, and C, and he can directly take output at this level. He cannot do internal to this connectivity, okay, inside the connections. Internally, he cannot test the logic by going into each and every cell and each and every combination logic gate. Now see, if you can, it is very evident that how much combination logic you have. For each combination logic, you are able to capture the output of the combination logic gate, and you are able to give input also directly. So you have direct access. These flip-flops have direct access to the combination logic gates inputs and outputs. Okay, our aim is also to verify both combination logic and sequential logic. So when you add addition, the only way to do DFT is to use the existing flip-flops in the design. We are using existing flip-flops in the design, okay, which are the fundamental blocks of driving the data and capturing the data. So one bit data can be stored in, or one bit of data can be toggled out. using this flop. So this particular flop is already connected physically, logically in the RTL code. Now you use this flip flop and create a scan path so that, let's say, you give this particular logic. Now once you convert this D flip flops into scan flip flops and you stitch all these flip flops into chain form, and you give it to the tool, ask the tool to generate patterns. What patterns? Or ask the tool to test this design. Okay, now what the tool will do, tool knows the truth table and everything of this design. Once you give the netlist and ask the tool to analyze the design, tool will analyze everything and it will form a schematic structure inside the design. Okay, it will create a flat model and it will see, okay, you have given me this design and libraries. Now I have a clear picture of each and every node of the cell, nodes and inputs and outputs of the entire design. Tool has full control on the design now. Now you are asking the tool, just test it. Okay, I have added another scan path for you and I have stitched the design. Now test it. Test me and tell that this entire combination logic and this entire flip flops, you test it and give me the report whether there are any faults within the design. Okay. Okay, you guys are understanding till this part? This is clear?
Yes, clear, sir.
Now, tool, once it takes this scan converted flaps design, okay, converted flop design, tool will see, okay, this is AND gate, right? Okay, AND gate truth table, okay, 1 and 1 high, all other combinations, it is 0. Now, I have to test this particular AND gate and many other gates here, including these flip-flops, to make sure that there is no stuck at inputs and outputs. Stuck at inputs and outputs. The tool, we have given algorithm. We already given algorithm to the tool to for this particular fault, stuck at fault. Okay, how to check that? Okay, we'll learn how to check that and the algorithm later. Okay, I'm just giving a glimpse here. Now, tool will to test the AND gate, this input and this input. Okay, first it will check one input. One input can be stuck at 0 or 1. That means stuck at ground, stuck to ground or stuck to high. Right? You want to verify it. You want to verify it for all the combination logic gates and sequential cells. That's your goal. Now tool will say to test whether it is stuck at 0 or 1. Let's say stuck at 0 here. What is the value tool has to give as input? If this node is stuck at 0, if you to prove that this is not stuck at 0, what is the value you have to give here? Anybody? Just think. There is an AND gate input and you want to prove that AND gate input is not stuck to ground or stuck to high, and now we assumed that, okay, it is prove that it is not stuck at ground, stuck at 0. Now what input you will give to that particular port to prove that it is not stuck at 0?
1.
1. Correct. Why? Because you want to prove the opposite value, right? When you give opposite value, then only tool will think, okay, if your 1 is passing out, that means it is not stuck at 0. If you give 0 again, you will not know whether it is stuck at 0 because you already gave 0 only. It will pass out 0 only. Correct? So you have to give the opposite value. Now you understand how the tool will think and behave for generating patterns or testing this logic. tool will create opposite values. And first, what it is doing, assuming a fault at that particular node and creating a opposite value as a pattern. Now, A, B, and C at a time, tool can verify at a time, because tool can assume entire SOC to be tested in a single stretch, because that's a tool. Okay, but if you have to do, you have to calculate one by one, one by one. You have to write a large truth table, draw a big truth table in your book for entire logic, and then you have to calculate, and you have to write a pattern for that. That's human brain. The machine, it's a assembler, it knows, it's a machine, it knows, it's a compiler, so it will directly decide the values in fraction of seconds, but not fraction of seconds. When you say a larger SOC design, when you have millions and trillions of logic gates, uh, this nanoseconds will become seconds, months, sorry, not months, at least days. Okay, when you have more combination logic gates, the tool will take a lot of time. The runtime of ATPG, the automatic test pattern generation, is very high when you have a larger combination logic gate count. Okay, the things uh, apart, that thing apart. Now you have given this design to the tool, and tool is trying to create patterns and test this logic by assuming fault at each and every node, here, everywhere. Okay, and it is driving that value through which, through scan input. Okay, you have decided to keep, okay, A B and C directly you are able to put, a tool will force the value from primary inputs. What about the internal pins? If you want to place something in the D input, okay, how do you place it? Because you want to place some value at this level, output of this particular flop, you want to place the value as some input to the this combination logic gate here. Now you have to program it, right? You should be able to have controllability on each and every node. To that, to do that, you have to have controllability on each and every flop and primary inputs and primary outputs. That's how DFT works. Gaining controllability. At the same time, observability. Okay, controllability is to gain access to place value at each input nodes of any logic. At the same time, observability is something you're able to capture that value out of the combination logic for which you have given as a input. By through the same scan input, you have given value to combination logic, and the logic has uh, given out value, and that has to be captured again properly without any issues. Then that means you have observability that particular on that particular node. Okay, so sorry guys, the motor sound is too high. Race bikes. Uh, Now this scan input to the scan output we have created in a scan chain format. So you directly feed in all the combination logic that is covered here. At a time you can test, tool can test at a time. So tool will create the pattern means A B C value, right? It will give you, okay, uh, the immediate logic of A B and C is going to AND gate and OR gate here. There is AND gate here, and this is there is OR gate here. Okay, likewise. So this is calculated by the tool and gives a pattern. Okay, 0 1 0. Okay, next, again here, this logic again, we are giving value from here, right? Again, the expected value out of this combination logic, a tool will assume, tool will calculate, and it will assume a pattern, and it will try to create a pattern the size of the flops. So if there is a three flip flops here, that means you can store 3 bits of data, right? So it will create only 3 bits of pattern. Okay, so only 3 bits of info can be stored and toggled. So in 3 clock cycles, 3 bits of data are stored and toggled and placed into the combination logic inputs, and combination logic output is captured in the next iteration. So that is how scan works. So this process I have explained simply, but there is a lot